Hello students, welcome to Jnanataranga program, the coaching class for CET and NEET classes. And in today's session, the discussion will be on hydrogen, S block and group 13 and 14 of P block, which you have learnt in first PU. And before we go to the questions, let us recall some of the important aspects or concepts which we have learnt in those topics. So the first topic is hydrogen, and you know the hydrogen exists has three isotopes: ordinary hydrogen, or it is also called protium, heavy hydrogen or deuterium, and radioactive hydrogen or tritium. Protium denoted as 1H1, deuterium 1H2 or D, and tritium 1H3 or T. For your information, the protium is the only isotope of hydrogen or the element in the periodic table which has 0 neutrons in its nucleus, and hydrogen can be manufactured by the electrolysis of acidified water. By passing electric current through water, you get hydrogen and oxygen gases. So the hydrogen can also be prepared by the reaction of steam or hydrocarbon with coke. So and C plus H2O gives you CO plus H2. The mixture of CO and H2 is called water gas, or it is also called synthetic gas or syngas, as it is used in the manufacture of methanol. And hydrides are the compounds of hydrogen with other elements. We have got different types of hydrides. The first one is ionic or salt-like or saline hydrides. These are normally formed by the reaction of alkali and alkaline earth metals. I mean to say the elements of group 1 and 2, which are highly electropositive, and the thermal stability of these hydrides, alkali metal hydrides as well as alkaline earth metal hydrides, decreases from lithium hydride to cesium hydride in alkali metals and CaH2 to BaH2 in alkaline earth metals. Then we have molecular or covalent hydrides formed by the elements of group 13 to 17, which are normally called non-metals, and these are divided into electron deficient hydrides like BH3, ALH3, etc., electron precise hydrides like CH4, and electron rich hydrides like NH3, H2O, HF, etc. In the electron deficient hydrides, the molecule or hydride is formed with inadequate number of electrons to write the conventional Lewis structure. If the electrons available are enough or sufficient to write the conventional Lewis dot structure, the hydride will be electron precise hydride, and in electron rich hydride you will have the excess electrons in the form of lone pair. In the hydrides such as NH3, you have got one lone pair of electron on nitrogen, and in H2O you have got two lone pairs of electrons on oxygen, and similarly in HF you have got three lone pairs of electrons on fluorine atom. And then you have metallic or interstitial hydrides. So these are normally formed by the transition elements or the D block elements, except the elements of groups 7, 8 and 9. They are also called non-stoichiometric hydrates, and these are formed when hydrogen gas is trapped into the cavities of or empty spaces between the metal atoms in the transition metal crystals. Since the number of cavities or the number of hydrogen atoms which are trapped is different from crystal to crystal, you cannot have a specific stoichiometry for the formula for these kind of hydrides, and hence they are called interstitial hydrides. Coming to hardness of water, temporary hardness of water is due to the bicarbonates of calcium and magnesium, and the temporary hardness can be removed by heating hard water. When you boil hard water, the soluble bicarbonates are converted into insoluble carbonates, and hence the precipitate of calcium carbonate can be filtered off to get the soft water. In Clark's method, the temporary hardness can be removed by adding calcium hydroxide. So the calcium hydroxide reacts with calcium bicarbonate and converts it into the precipitate of calcium carbonate, which can be filtered off. The permanent hardness of water is due to chlorides and sulfates of calcium and magnesium, and it can be removed by adding soda lime. In soda lime method, it can be removed by adding sodium carbonate. So during which the bicarbonates of and chlorides of calcium and magnesium react with what is called Na2CO3 to form carbonates of calcium and magnesium. And in the ion exchange method, calcium and magnesium ions are exchanged by the addition of inorganic ion exchangers such as zeolite. So that is Na2Z, where Z is nothing but hydrated aluminum silicate. So the equation for the ion exchange method is Na2Z, which is called sodium zeolite. When it is added to hard water, the calcium ion present in the hard water gets exchanged, or it replaces sodium to form CaZ, and thereby the permanent hardness of water can be removed. And in the S block mainly consists of the elements of group 1 and 2. The first group elements or metals are normally lithium, sodium, potassium, rubidium, cesium and francium of group 1. They are called alkali metals. So alkali metals, the name is derived because the hydroxides of these metals are water soluble bases. So the elements such as beryllium, magnesium, calcium, strontium and barium of group 2, they are called alkaline earth metals. So alkali metals are paramagnetic because of NS1 configuration, in the sense the valence shell of these elements have one electron. On the other hand, alkali metal ions, which are produced by the loss of electron present in the valence shell, are diamagnetic and colorless due to their noble gas configuration with no unpaired electrons. Degree of hydration of alkali metal ions decreases from lithium to cesium. So the relative ionic radii in water also decreases in the same order. The extent of hydration depends on the size. So the lithium ion is the smallest alkali metal ion and is hydrated to a larger extent, and therefore the ionic radii in water decreases from lithium to cesium with increase in size of the cation. Lithium is the lightest, least fusible, least dense and soft of all the alkali metals. So and lithium, it is the lightest metal, and normally these alkali metals are placed in kerosene because of their reaction with H2O. But lithium cannot be stored under water. Cannot be stored under kerosene because it is lightest metal and floats on the surface of the kerosene, and hence it is wrapped in paraffin wax. Although lithium has highest ionization enthalpy as you know is the amount of energy required to remove the electron from the outermost valence shell. Normally in any group, the topmost element will have highest ionization energy. Lithium, being the top element in the group 1, will have highest ionization energy, but still it is the strongest reducing agent because of its large heat of hydration, which is sufficient or which compensates for its high ionization enthalpy. And most metallic elements in the periodic table, because when you move from top to bottom in the first group of alkali metals, the metallic character or tendency to lose electrons or electropositivity as we call increases from lithium to cesium, and hence the most metallic elements in the periodic table are cesium and of course francium. The solubility, the basic strength of oxides increases from lithium oxide to cesium oxide, and similarly the solubility, stability and basic strength of hydroxides also increases in the same order from lithium hydroxide to what is called cesium hydroxide. I mean to say, cesium hydroxide is the strongest alkali metal hydroxide among the first group metal hydroxides. The stability of peroxides and superoxides also increases from sodium oxide to cesium oxide in the same order, and then the superoxides both will go in the same order. Stability and solubility of carbonates, nitrates, bicarbonates increase in the same order from lithium carbonate to cesium carbonate, lithium nitrate to cesium nitrate, and lithium bicarbonate to cesium bicarbonate. So when you move from lithium to cesium in the alkali metal group, electropositivity, atomic radii, atomic volume, reducing power, solubility of salts and density show an increasing trend. In alkaline earth metals, the properties such as metallic nature, reducing nature, reactivity, electropositive character and ionic nature of the compounds increase from beryllium to barium. The solubility of chlorides, bromides, iodides decrease in the order from magnesium to what is called barium. So the MgX2, CaX2, SrX2 and then BaX2. So that means to say halides of alkaline earth metals where X is equal to Cl, chlorine, bromine or iodine. The basic character of oxides, hydroxides increase in the same order from beryllium to barium, and similarly from barium hydroxide to barium hydroxide. The thermal stability of carbonates and sulfates also increase down the group from beryllium to barium, and the order is from BeCO3 to BaCO3 and similarly from BeSO4 to BaSO4. Coming to the elements of group 13 and 14 of P block. So the group 13 members are boron, aluminium, gallium, indium and thallium, and the general configuration, because they are the 13th group members, and will be NS2NP1. The hydrates of group 13 are normally not formed by the direct reaction with H2. Group 13 elements form trihalides except thallium, and halides of boron are electron deficient compounds. They are normally formed with inadequate number of electrons, and hence they act as Lewis acids. The acidic strength of boron halides will increase from BF3 to Bi3. Similarly, the group 14 members are carbon, silicon, germanium, tin, lead, and its general configuration is NS2NP2. Catenation is the property which is found with group 14 elements, and carbon exhibits maximum catenation property because of high stability of CC bond, and it decreases as we go down the 14th group, and virtually tin and lead do not show any kind of catenation property. And coming to carbon, not only carbon, the topmost member of any element in the periodic table in each group will have some anomalous properties, and the 14th group the topmost element being carbon, also exhibits some of the most important anomalous properties. Due to non-availability of d orbitals, the covalency of carbon cannot go beyond 4, and carbon has the unique ability to form p-pi multiple bonds with itself or with atoms of small size and high electronegativity such as oxygen and nitrogen. Heavier elements do not form p-pi multiple bonds, and the most important allotropic forms of carbon and diamond, carbon or diamond and graphite, which are considered as crystalline allotropic forms, and the amorphous allotropic forms of carbon are normally coal, coke, charcoal, lamp black, carbon black, etc. And almost all the members of 14th group exhibit allotropy. Silicon exhibits allotropy in the form of crystalline and amorphous silicon. Similarly, germanium also will have two crystalline forms, and tin exhibits allotropy in the form of grey tin, white tin and rhombic tin. And lastly, some of the gaseous fuels, the composition of gaseous fuels, if I have to mention, water gas, as I told you already, is also a mixture of CO plus H2, it is also called synthesis gas. Semi-water gas has the composition CO plus H2 plus N2. Natural gas mainly contains methane, and producer gas will have CO plus N2, and LPG gas, liquefied petroleum gas, will have mainly butane plus isobutane. And now coming to the questions, the decomposition of hydrogen peroxide is retarded by, the options are H3PO4, which is called phosphoric acid, alcohol, option C acetanilide, and D all of these. So the hydrogen peroxide is basically an unstable compound which slowly decomposes into H2O and O2. The decomposition of hydrogen peroxide can be retarded or can be slowed down by the addition of either phosphoric acid or alcohol or acetanilide. All these substances retard the decomposition of hydrogen peroxide, and hence the correct option becomes option D. Then the question number 2, which of the following cannot be oxidized by H2O2? Option A Ki plus HCl, option B O3, option C PBS lead sulfide, option D sodium sulfite. H2O2, as I said, on decomposition liberates oxygen, hence it acts as an oxidizing agent, but ozone is more powerful oxidizing agent than hydrogen peroxide, and hence when ozone is made to react with H2O2, so the H2O2 reduces ozone to H2O and O2, and therefore so the correct option becomes option B, that is ozone, which is a more powerful oxidizing agent compared to H2O2. And then in the question number 3, you have to match the list 1 with the list 2. You have been given heavy water, temporary hard water, soft water, permanent hard water in list 1. Heavy water, as I said already, is due to the presence of sulfates and chlorides of magnesium and calcium in water. That means the heavy water matches with D in the list 2. Temporary hard water is because of the the question number 3, we have to match the items in the list 1 with list 2. Heavy water is also called deuterium oxide, and hence the heavy water matches with C in list 2. temporary hard water is due to the presence of bicarbonates of magnesium and calcium in water, and 2 in list 1 matches with A. Soft water is considered as the water with no dissolved salts or no ions in the solution in water, and hence the 3 in list 1 matches with option B. The permanent hard water, as I said, is due to sulfates and chlorides of magnesium and calcium, and therefore the correct option becomes option D for the question number 3. So the fourth one, commercial 10 volume of H2O2 in a solution with strength of approximately 30%, 3%, 1% and 10%. Normally the strength of volume, strength of hydrogen peroxide is expressed in terms of volume of oxygen liberated by 1 ml of hydrogen peroxide solution at STP. If I say 10 volume of H2O2 solution means 1 ml of this sample of H2O2 on decomposition gives 10 ml of oxygen gas at NTP, or 1 liter of the sample of solution will liberate 10 liters of oxygen gas at STP. So in the equation 2 moles of H2O2, that means to say 2 into 34, which happens to be the molar mass of H2O2, equals 68 gram of H2O2 on decomposition gives you 1 mole of oxygen gas at STP. 1 mole of oxygen gas, you know, has a volume of 22.4 liters at STP. Obviously 22.4 liters of oxygen gas at STP is obtained from 68 gram of hydrogen peroxide. Therefore 10 liters of oxygen gas at STP will be obtained from 68 by 22.4 into 10, which gives you 30.357 gram of hydrogen peroxide. The strength of hydrogen peroxide in 10 volume of hydrogen H2O2 solution is 30.357 gram per liter, which is equal to 3.057 gram per 100 ml, and therefore the 10 volume hydrogen peroxide is approximately 3% solution of H2O2. The correct option becomes option B. The question number 5, H2O2 when added to a solution containing KMNO4 and H2SO4. KMNO4 mixed with sulfuric acid is called acidified KMNO4, which is a powerful oxidizing agent. Since acidified KMNO4 is a powerful oxidizing agent, H2O2 will have to undergo oxidation by reacting with oxygen produced from KMNO4, forming H2O and O2. Since it undergoes oxidation, in the reaction H2O2 is considered as a reducing agent, and hence the correct option is option B. The question number 6, deuterium oxide or D2O. This is also called heavy water, is used in nuclear reactors as the options are fuel, source of deuteron, source of alpha particle and moderator. In the nuclear reactors, the role of heavy water or deuterium oxide is to slow down the fast moving neutrons. So that phenomenon is called moderator action. D2O is used as a moderator to slow down the fast moving neutrons, and hence the correct answer is option D. In the question number 7, the reaction H2S plus H2O2 arrow mark S plus H2O manifests the acidic nature of H2O2, alkaline nature of H2O2, oxidizing action of H2O2 and reducing action of H2O2. In the reaction, H2S gets oxidized into sulfur. H2S is converted into sulfur and H2O2 is converted into H2O, and H2S is oxidized to sulfur by H2O2, and hence so the H2O2 acts as an oxidizing agent in this reaction, and the correct answer is option C. In the question number 8, hydrogen resembles halogens in many aspects for which the several factors are responsible, and the most important factor among that you have to find out. Option A is its tendency to lose electron from a cation. Option B is its tendency to gain single electron in its valence shell to attain stable electronic configuration, its low negative electron gain enthalpy value, and its small size. Hydrogen is one element which can be placed in first group as well as 17th group. It is placed with alkali metals because of its 1s1 configuration. Hydrogen has the ability to lose electron to form H plus, and therefore it is placed in first group. When it comes to 17th group is concerned, which is the halogen family, all halogens will gain one electron and form the stable inert gas configuration, and therefore hydrogen also gains one electron to form H minus ion, which is called hydride ion. Its tendency to gain electron in its valence shell and attains the stable 1s2 configuration is the reason for its resemblance with halogen family, and obviously the correct answer is option B. Coming to question number 9, metal hydrides are ionic, covalent and molecular in nature. Among lithium hydride, sodium hydride, potassium hydride, rubidium hydride and cesium hydride, the correct order of increasing ionic character. So the options are given as A, B, C, D. The ionic hydrides are normally formed by the electropositive metals with hydrogen, and the electropositive character, as you know, increases from lithium to cesium due to increase in size. With increase in size, cesium has a tendency to lose the electron very easily, and therefore it is considered as highly electropositive metal. And the decrease in ionization enthalpy is again because of the increase in size from lithium to cesium. Obviously, cesium hydride will be highly what is called ionic character, and lithium, the ionic character of alkali metal hydrides will definitely increase from lithium to cesium, and therefore the correct option becomes option B. In the question number 10, HOH bond angle in water molecule. You know, water has what is called the bent structure like O, H and then H. The bond angle is 104.5 degree, and that is because of the presence of two lone pairs of electrons on oxygen atom. The hybridization in oxygen of water molecule is sp3. Normally in case of sp3 hybridization, the bond angle expected is 109 degrees 28 minutes. But because of the presence of lone pair of electrons on the oxygen atom, there will be a repulsion between lone pair and bond pair, and because of the repulsion, the bond angle is reduced from 108 degree to 104.5, and hence the correct option becomes option D. In the question number 11, water contracts on heating from what is called 200 degrees centigrade, from 0 to 4 to 273, and then from 10 to 20. Normally when any liquid or a solid is heated, its volume increases. However, water has extensive hydrogen bonding when it is freezed into ice. Because of extensive hydrogen bonding, So the oxygen atoms in ice are tetrahedrally arranged with many vacant spaces. So the vacant space present in ice is responsible for low density of ice, and that's the reason why ice floats on the surface of water. Anyway, when you heat ice or water from 0 degree centigrade to 4 degree centigrade, instead of expansion or instead of increase in volume, the volume decreases because the hydrogen bonds are broken and the water molecules will occupy those vacant spaces, thereby leading to contraction. However, this effect is observed up to 4 degree centigrade, and beyond 4 degree centigrade the normal increase or expansion due to heating effect would dominate over the decrease in volume caused because of the breakage of hydrogen bonds, and therefore at 4 degree centigrade water will have what is called minimum volume or maximum density, and therefore the correct option for question number 11 is option B. To question number 12, 2 gram of aluminium metal is treated separately with excess of dilute sulfuric acid as well as sodium hydroxide solution, and the ratio of volume of hydrogen evolved is option A 2:3, option B 1:1, option C 2:1, option D 1:2. So when aluminum is made to react with sodium hydroxide solution, you get NaAlO2 plus 3H2, as in the equation you get 3 moles of hydrogen by the reaction of 2 moles of aluminium, and the same 2 moles of aluminium would react with sulfuric acid, liberating the same 3 moles of hydrogen gas. Obviously, the ratio of volumes of hydrogen evolved will be 3:3 or 1:1, and hence the correct option is option B. To question number 13, when 2 ice cubes are pressed over each other, they unite to form 1 cube, and which of the following force is responsible to hold them together? And as I said, ice has got extensive hydrogen bonding. Because of the tendency to form more of hydrogen bonds, the ice cubes unite together, and hence the correct option for question number 33 would be option A, which says hydrogen bond formation. Into question number 14, the number of moles of hydrogen gas in 0.224 liters of hydrogen gas at STP, that is 273 Kelvin and 1 atmospheric pressure is, the options are 0.1, 0.01, 0.001 and then 1. And as you all know, the molar volume of any gas is 22.4 liters at STP, that is the volume occupied by 1 mole of any gas at STP. That means to say 22.4 liters of hydrogen gas at STP corresponds to 1 mole of hydrogen gas. Obviously 0.224 liters of hydrogen gas at STP will have 1 divided by 22.4 into 0.224, that is 0.01 moles, and hence the correct answer is option B. Into question number 15, the molarity of pure water at 277 Kelvin. So the options are 55.5 moles, 1 mole, 2.5 mole, 5 molar. Molarity represents the number of moles per liter or per decimeter cube. So if you take water at 277 Kelvin, the density of water is 1 gram per ml. That means to say 1 ml of water would weigh 1 gram, and obviously 1000 ml or 1 liter of water would weigh 1000 grams. When you take pure water, 1 liter of pure water, the mass of 1 liter of pure water will become 1000 gram when it is maintained at 277 Kelvin. The number of moles obviously is equal to mass by molar mass of H2O. 1000 grams divided by molar mass of H2O is 18, and that gives you 55.55 moles per liter, which is nothing but the molarity. and hence the correct option is option A. Into 16, the correct order of OO bond length in oxygen, H2O2 and O3 are, the options are given. You know, in O2 molecule there is a double bond between two oxygen atoms, and the structure of H2O2 can be written like this. You have got a single bond between two oxygen atoms, whereas in ozone you have got a partial double bond because of resonance. Obviously a double bond will be shorter than a single bond, and since ozone has got partial double bond, this is oxygen in the ozone, because ozone is a triatomic molecule and ozone has partial double bond. As I said, the longest bond will be the single bond in H2O2, and then comes the partial double bond in ozone, and then comes the clear double bond in O3, and therefore the correct option is what is called option C. And in the question number 17, which of the following terms is not correct for hydrogen? Its molecule is diatomic, which is very much a correct statement, because the formula of hydrogen is normally H2. It exists both as H plus and H minus ion in different chemical compounds. Definitely that is also a valid point. It is the only species which has no neutrons in the nucleus, that is protium or 1H1 has 0 neutrons in its nucleus. That is also a correct statement. And option D, which says heavy water is unstable because hydrogen is substituted by the isotope deuterium. This is, heavy water is more stable than H2O, and the option D is the incorrect statement, and therefore becomes the correct answer for question number 17. Coming to question number 18, which are the following alkali metal ions will have the lowest mobility in aqueous solution? The options are Li plus, Na plus, K plus and Cs plus. So lithium plus ion, due to extensive hydrogen, has lowest ionic mobility. The extensive hydration of lithium plus ion is because of its smaller size, and therefore, so because of excessive hydration, the lithium plus ion will have lowest mobility, and the correct option is option A. In the question number 19, which of the following has the highest melting point? So for the same alkali metal, the melting points of halides will decrease from fluorides, then to chlorides, and then bromides and iodides, because the lattice energies decrease as the size of halide ion increases. So and therefore the sodium fluoride with highest lattice energy will be having highest melting point, and the correct option is option B. In the question number 20, the lithium is the strongest reducing agent among alkali metals due to which of the following factors? So in the first group, the ionization enthalpy decreases from lithium to cesium. Lithium, being the topmost element in the first group, will have highest ionization enthalpy. Though it has highest ionization enthalpy, because of its extensive hydration energy or highest hydration energy, which overcompensates for its high ionization enthalpy, the lithium undergoes oxidation easily, and therefore it can act as a powerful reducing agent, and that is one of the anomalous property of lithium, and therefore the correct answer is option C. Into the question number 21, sodium nitrate decomposes above 800 degrees centigrade to give, as it is written in the equation, sodium nitrate on heating above 800 degrees centigrade decomposes into sodium nitrite plus O2. Among alkali metal nitrates, only lithium nitrate on heating evolves NO2 and O2. All other alkali metal nitrates give only oxygen on heating, and obviously the correct answer is option B, that is O2. The 22nd question, which of the following bicarbonates doesn't exist as a solid? And the lithium hydrogen carbonate or lithium bicarbonate is very much unstable among alkali metal hydrogen carbonates, and it exists only in solution, and therefore the correct option is option D. In the 23rd question, ionic hydride is not formed by beryllium, calcium, barium and strontium. Hydrides of beryllium and magnesium are covalent. BeH2 is a covalent hydride which exists as a polymeric solid, in which each hydrogen atom is involved in 3-centered bond and exists as a bridge between the two beryllium atoms on both sides, and therefore, so the option A, beryllium hydride, is not an ionic hydride, and therefore option A is the correct answer. So the question number 24, which of the following has exceptionally high melting point? The options are MgO, NaOH, NaCl and KCl. Higher the charge on the ions, in fact lattice energy is the amount of energy which is required to break 1 mole of ionic solid into its constituent ions. So lattice energy is directly proportional to charge on the ions. So among the options which are given, magnesium has 2+ charge, and therefore so the lattice energy and the melting point of a bivalent ionic solid, which is MgO in the options, will be more than that of the univalent ionic solids, and hence the correct option is option A. In the question number 25, the ion having highest mobility in aqueous solution. The options are beryllium 2+, Mg2+, Ca2+, and then Ba2+. So when you move from top to bottom in the alkaline earth metals, the extent of hydration gradually decreases. Barium at the bottom of the group is least hydrated, and therefore the size becomes lesser than any other alkaline earth metal atoms. Obviously that will have the highest ionic mobility, and hence the correct option is option D, that is Ba2+. Question number 26, identify the correct statement. Gypsum is obtained by heating plaster of Paris. POP can be obtained by the hydration of gypsum. POP can be obtained by partial oxidation of gypsum, and gypsum contains lower percentage of calcium than plaster of Paris. So we have to find out the correct statement here, and you know gypsum is CaSO4.2H2O, calcium sulfate dihydrate, whereas plaster of Paris is 2CaSO4H2O or CaSO4 half H2O, which is called calcium sulfate hemihydrate. So and the obviously from the formula or molar mass calculations, it can be shown that gypsum contains a lower percentage of calcium than plaster of Paris, and the correct statement among all those is the option D. In the 27th question, which of the following has correct increasing basic strength? So the oxides of alkaline earth metals are given, and in the alkaline earth metals the basic character of oxides increases down the group from beryllium to what is called barium. That means to say BeO less basic compared to MgO, less basic compared to BaO, and then the CaO, and then the BaO will have the maximum basic strength. and then therefore the correct order is from BeO to BeO. Obviously the option B is the correct answer. In the question number 28, the pair of compounds which cannot exist together in the solution. The options are sodium bicarbonate and sodium hydroxide, option B sodium bicarbonate and H2O, C sodium bicarbonate and Na2CO3, D Na2CO3 and NaOH. So the sodium bicarbonate is an acidic salt of carbonic acid, that is H2CO3, and therefore it will react with NaOH producing Na2CO3 and H2O as it is there in the equation, and hence the correct option is option A, sodium bicarbonate and NaOH cannot exist together. In the question number 29, common table salt, that is sodium chloride, becomes moist and doesn't pour so easily in rainy season. And the reasons are that it contains magnesium chloride, it contains magnesium carbonate, it melts slightly in rainy season, sodium chloride is hygroscopic. Normally the table salt contains impurity in the form of MgCl2, which is a hygroscopic solid. Hygroscopic solid absorbs atmospheric moisture, and therefore so the common salt, because of the presence of hygroscopic magnesium chloride, becomes moist and doesn't pour so easily in the rainy season. Obviously the correct answer is option A. And in the question number 30, which of the following is true about calcium hydroxide? Option A, it is used in the preparation of bleaching powder. It is a light blue solid. It doesn't possess disinfectant property, or it is used in the manufacture of cement. Calcium hydroxide, when it is made to react with chlorine, you get calcium oxychloride, which is considered as bleaching powder. Bleaching powder or calcium oxychloride can be obtained by passing chlorine gas over slaked lime or calcium hydroxide, and hence the option A is the correct option. The question number 31, when a crystal of caustic soda is exposed to air, a liquid layer is deposited because sodium hydroxide is considered as a deliquescent solid. Deliquescence is a phenomenon in which a solid absorbs atmospheric moisture and gets converted into liquid state. Sodium hydroxide is deliquescent, and when it is exposed to atmospheric air, it absorbs moisture and CO2 present in the atmosphere and forms sodium carbonate, and therefore the correct option is option B, which says the crystal absorbs moisture and CO2 from the atmosphere. Question number 32, if sodium hydroxide is added to an aqueous solution of Zn2 plus ions, a white precipitate appears, and on adding excess of sodium hydroxide, the precipitate dissolves. In this solution, zinc exists in, the options are cationic and anionic part, no zinc left in the solution, cationic part and anionic part. When sodium hydroxide is added to the salt solution of zinc ions, you get a white precipitate of zinc hydroxide. This zinc hydroxide is soluble in excess of NaOH, and therefore when we add excess of NaOH, the white precipitate which was formed initially dissolves in excess of NaOH to form Na2ZnO2, which is called sodium zincate. This sodium zincate is a clear solution. In solution it gives sodium plus ion and ZnO2 2 minus, that is zincate ion, which is nothing but the anion. So the zinc comes out in the form of zincate ion, that is anion, and therefore the correct option is option D. Question number 32, beryllium shows diagonal relationship with aluminium. Which of the following similarity is incorrect? The diagonal relationship is the similarity in the properties of elements of second period with those elements placed diagonally opposite to them. So beryllium and aluminum is one such pair which exists diagonal relationship, and the beryllium forms berylates and aluminum forms aluminates. That is one common phenomenon which is found with both beryllium and aluminum. Beryllium hydroxide, like AlOH thrice, is basic. Beryllium hydroxide and aluminum hydroxide, both hydroxides are amphoteric in nature. That means to say, a substance is said to be amphoteric if it behaves both, or it exhibits both acidic and basic properties. Both beryllium hydroxide and aluminum hydroxide are amphoteric, and this is the incorrect statement regarding the diagonal relationship, and hence the option B is the correct answer. And then into the question number 34, the power of halides of boron to act as Lewis acids decreases in the order. So you have been given BF3, BCl3 and BBr3. You have to arrange from the strong acid to weak acid, or decreasing order of acidic strength. Halides of boron, that is BF3 or BCl3 or BBr3, are electron deficient compounds, and therefore they act as Lewis acids. The acidic strength of these boron halides decreases from iodides to fluorides, and therefore in the options, option B, which says BBr3 more acidic than BCl3 more acidic than BF3, that becomes the correct option. Then coming to question number 35, aluminum is more reactive than iron, but aluminum is less easily corroded than iron. So the rusting of iron happens rapidly, whereas aluminum is not so easily corroded. The reasons are, it is a noble metal, the option A, and in the option B, the oxygen forms a protective oxide layer on aluminum. Option C, iron undergoes reaction easily with water. Option D, iron forms mono and divalent ions. When aluminum is exposed to atmospheric air, the surface aluminum atoms undergo oxidation to form a protective layer of aluminum oxide, and that prevents the metal from further corrosion, and hence the correct option is option B. Into question number 36, the ionization enthalpy among group 13 members. Follow the order. See, usually ionization energy or enthalpy is considered as energy required to remove the outermost electron from an isolated gaseous atom. Normally the ionization enthalpy values decrease when you move down a group because of the increase in size. In the boron family, so the gallium, which lies below aluminum, has more of ionization enthalpy compared to aluminum because of its small size and effective nuclear charge of gallium. That means to say, that is caused because of poor shielding of 3d electrons present in gallium, and this results in greater attractive force by the nucleus of gallium on the valence electrons. Obviously more energy is required to remove the electron from the outermost shell of gallium compared to aluminum, and hence the correct sequence in the decreasing order becomes boron, gallium, and then aluminum, and then thallium, and the option C is the correct one. In the question number 37, the aluminum salt commonly used to stop bleeding is the aluminum sulfate, potassium sulfate, aluminum chloride, and aluminum fluoride. The potash alum, is a double salt. Double salt is normally a mixture of two simple inorganic salts having the composition K2SO4, Al2SO4 thrice 24H2O. Normally potash alum is employed as styptic. that means to say to stop bleeding from cut wounds. So the potassium and aluminum ions present in the potash alum coagulate the negatively charged blood particles and stop further bleeding of the blood, and that kind of action is called styptic action, and the potash alum is normally employed for that purpose, and hence the correct option is option B. The question number 38, the diamond and graphite are shown to be the allotropic forms of carbon by the fact that diamond is hard but graphite is soft. Normally the allotropic forms are different physical forms of the same element, but the similarity in chemical properties. Diamond is transparent while graphite is opaque. This no way is the correct answer. They have different crystal structures. Crystal structure may be different, but when both diamond and graphite are burnt, so they are the allotropic forms of carbon, and hence carbon present in both diamond and graphite burns in presence of oxygen to produce CO2 gas. Because of this similarity in the chemical property, you can consider diamond and graphite are as the allotropic forms of carbon, and hence option D becomes the correct answer. The question number 39, the hydroxide which is best soluble in water. You have been given alkali metal hydroxides here, barium hydroxide, magnesium hydroxide, strontium hydroxide and calcium hydroxide. The solubility of hydroxides increases from top to bottom when you move down along the alkaline earth metal group because of the decrease in lattice energy. So the bottommost element is barium, and therefore the barium hydroxide will have what is called maximum solubility, and the correct option is option A. In the question number 40, which of the following is used in high temperature thermometry? The options are sodium, gallium, thallium and mercury. Gallium is one such metal which remains as liquid over a wide range of temperature, that is from 303 Kelvin to 2510 Kelvin. And this metal also remains as liquid even when it is cooled below its freezing point of 303 Kelvin. And hence, since it exists as a liquid over a wide range of temperature, it is used in quartz thermostats for measuring high temperatures. Into question number 41, catenation, that is called linking of similar atoms, depends on size and electronic configuration of atom. The tendency of catenation in group 14 elements follows the order. So the options are given as A, B, C, D, and the catenation tendency, as I said in the earlier synopsis, the catenation property depends on the strength of element bond, and among group 14 elements the carbon-carbon bond enthalpy is maximum. It has got high bond enthalpy and it decreases from carbon to tin. Carbon also has the strong ability to form p-pi multiple bonds with itself or with more electronegative elements such as nitrogen and oxygen, and hence the correct option becomes option B, that is C more than Si more than germanium and almost equal to tin, and the correct answer for the question number 41 is option B. Into question number 42, hydrogen will not reduce. The options are heated cupric oxide, heated ferric oxide, heated stannic oxide, heated aluminum oxide. You know, aluminum is less electropositive than hydrogen is less electropositive than aluminium, and hence hydrogen will not reduce the heated Al2O3, and hence the correct option is option D, that is heated aluminum oxide. In the question number 43, which statement is false? That means to say incorrect statement. Option A, water gas is a mixture of hydrogen and carbon monoxide. Producer gas is a mixture of carbon monoxide and nitrogen. Water gas is a mixture of water vapor and hydrogen. Natural gas consists of methane, ethane and gaseous hydrocarbons. As I said, water gas is a mixture of carbon monoxide and hydrogen. It is also called syngas as it is used in the synthesis of methanol. And therefore, the incorrect statement, producer gas definitely is a mixture of carbon monoxide and nitrogen, and natural gas definitely will have methane, ethane and gaseous hydrocarbons. The false or incorrect statement among the four options which are given are the option C, which says water vapor and hydrogen is the constituent of water gas, and therefore the correct option is option C. 44. The boron halides behave as Lewis acids because option A, they are covalent compounds. Option B, have only 6 electrons in the valence shell. Option C, they are ionic compounds. Option D, have a lone pair of electrons on boron atoms. So boron halides, that is BS3, have only 6 electrons, 3 from boron and the 3 from the halogen atoms around the central boron atom, because the electron configuration of boron, as you know, 1s2, 2s2, 2p1. So therefore 3 electrons of boron will form bonds with 3 halogen atoms, and thus the octet around the central boron atom is not complete. Because of incomplete octet, boron behaves as electron deficient compound or a Lewis acid, and the correct option is option B. In the question number 45, graphite conducts electricity because of option A, weak van der Waals force between layers, covalent bonding between carbon atoms of layers, delocalized electrons in each layer. Option D, sp2 hybridization of carbon atoms in a layer. You know, graphite and diamond are the two allotropic forms, crystalline allotropic forms of carbon. Diamond has the sp3 hybridization, whereas graphite has sp2 hybridization or sp2 hybridized carbon atoms. Because of sp2 hybridization, each carbon is bonded to 3 more carbon atoms with 3 electrons, and the 4th electron of each carbon atom is not involved in bonding and is considered as a delocalized electron, and hence it moves around the hexagonal network of carbon atoms in the graphite, and the conductivity of graphite is due to these kind of delocalized electrons within a layer. In diamond, since all the carbon atoms are involved in bonding, no such free electrons are present, and therefore diamond, for your information, is an insulator, and diamond again is considered as the hardest substance. Anyway, for this question, the question number 45, the conductivity of graphite is because of the presence of delocalized electrons, and therefore option D becomes the correct answer. Option C, delocalized electron in each layer, becomes the correct answer. In the question number 46, gas A is bubbled through slaked lime. When a white precipitate is formed, on prolonged bubbling the precipitate dissolves. On heating the resulting solution, the precipitate appears back. with the evolution of gas B. The gases A and B respectively are. So the options are given as CO and CO, CO2 and CO, CO and CO2, CO2 and CO2. When you pass a gas A through slaked lime, that is nothing but calcium hydroxide, you are getting a precipitate in the form of carbonate. Definitely among the options which are given, it should be either CO2 or CO. The precipitate is formed only when CO2 gas is passed through calcium hydroxide, and therefore, so the gas A must become definitely CO2. And when you pass excess of CO2 gas through CaCO3, the precipitate of calcium carbonate is converted into soluble bicarbonate, calcium bicarbonate, and therefore precipitate naturally dissolves. And when you heat that resulting calcium bicarbonate solution, you get back the precipitate because the soluble bicarbonate is converted into insoluble carbonate along with the liberation of what is called CO2 gas, which happens to be the gas B. And hence gas A and gas B are both carbon dioxide or CO2, and the correct option is option D. In the question number 47, which of the following represents the electronic configuration of most electropositive element? So the inert gas configuration with 2s1, 2s2, 6s1 and 6s2 options are given. And you know very well the alkali metals in the periodic table are the most electropositive, and the electropositive character definitely increases down the group. The element at the bottom of first group will have highest electropositivity, and xenon 6s1 being the largest what is called alkali metal atom will be the most electropositive element, and therefore the correct option is option C. 48. The sodium ordinarily doesn't show an oxidation state of +2 because when I write the electron configuration of sodium, we write it as 1s2, 2s2, 2p6 and then 3s1 or neon 3s1. The electron present in the 3s orbital can be easily removed because it is the only electron present in the third shell, and after removal the ion or Na plus ion will have the stable inert gas configuration. So the first ionization enthalpy of sodium will be naturally low, whereas for the removal of second electron you need much higher energy because you are removing the second electron from the stable inert gas configuration, and therefore it has got a high value of second ionization enthalpy, and hence it doesn't show the +2 oxidation state because you have to use more energy to remove the second electron from the sodium atom, and hence the correct option is option B. Into question number 49, which of the following compounds has both ionic and covalent bonds? Among the four options which are given, KCl, KCN, NaH and NaI, you know potassium cyanide is a compound which ionization produces K plus and Cn minus ions, in which you have got a triple covalent bond between carbon and nitrogen, and the bond between K plus and Cn minus ions is ionic, and therefore KCN or option B, the potassium cyanide compound, is an example of a compound which has both ionic and covalent bonds. Into question number 50, the chloride of an element A gives neutral solution in water. In the periodic table, the element A belongs to option A first group, B third group, fifth group, and then D first transition series. The hydroxides of first group, that is alkali metals, are normally strong bases, and when the chloride of an element gives a neutral solution, the chloride of alkali metal definitely in solution undergoes hydrolysis, producing a strong base, that is alkali metal hydroxide, and HCl, which is a strong acid. Since you get a strong acid and strong base in solution, definitely it will be neutral, and therefore the chlorides of first group elements are the salts of strong acids and strong bases and produce neutral solutions on hydrolysis, and obviously the correct answer is option A. Into question number 51. Which of the following order presents the correct sequence of increasing basic nature of given oxides? So the oxides which are given are Al2O3, MgO, Na2O, and then K2O. So you find the alkali metal oxides, alkaline metal oxides, as well as the aluminum oxide also in the options. When you move across a period or from left to right along the periodic table, ionization energy values increase because of the addition of electrons to the same electronic shell, and therefore the electropositive nature of metal naturally decreases. The ease of formation of ion also decreases, and hence the basic character decreases. That means to say, the aluminum, which is aluminum oxide, so definitely will be least basic, and then the alkali metal oxides, the basic character of alkali metal oxides increases from lithium to cesium, and obviously so aluminum oxide is least basic, and then comes alkaline earth metal oxide, that is MgO, and then comes Na2O, and then K2O. The correct option is option A. And then the question number 52. You have to identify the correct statement among the four options. The first option says elemental sodium can be prepared and isolated by electrolyzing an aqueous solution of sodium chloride. Definitely this is a wrong statement, because you can get sodium by the electrolysis of molten NaCl and not aqueous solution of NaCl. Elemental sodium is a strong oxidizing agent. This is again incorrect statement, because sodium can easily undergo oxidation and it can act as a reducing agent. Elemental sodium is insoluble in ammonium. No, it is very much soluble in ammonia. And option D says elemental sodium is easily oxidized because of low ionization potential, and therefore it acts as a reducing agent, and the option D is the correct statement regarding the sodium, and therefore the correct answer is option D. Into question number 53. Sodium sulfate is soluble in water, whereas barium sulfate is sparingly soluble in water, because the options are the hydration energy of sodium sulfate is more than its lattice energy. The lattice energy has no role to play in its solubility. Option C says the hydration energy of sodium sulfate is less than its lattice energy, and option D is none of these. Normally, if lattice energy is less than hydration energy, the ionic compound will be very much soluble in water. Since the lattice energy of sodium sulfate is less than its hydration energy, or hydration energy is more than its lattice energy, the sodium sulfate is very much soluble in water, and hence the correct option is option A. Into question number 54. Alkaline earth metals form dipositive ions instead of unipositive ions, because the option A, dipositive ions carry more charge. Option B says the second ionization enthalpies are not different from first ionization enthalpy. Option C says unipositive ions do not have stable configuration, and option D says compounds containing di-positive ions have more lattice energy. And we know the lattice energy is directly proportional to what is called charge on the ion and is inversely proportional to size. Therefore, so the alkaline earth metals form di-positive ions because of the higher lattice energies compared to what is called unipositive ions. Alkaline earth metals will have 2 plus charge and therefore they form di-positive ions, and hence the correct option is option D, that is the compounds containing di-positive ions will have more of lattice energy. Into question number 55. The value of X, that is the number of molecules of water which gets hydrated with salt, is maximum for option A MgSO4XH2O, option B CaSO4.XH2O, option C BaSO4.XH2O, and option D says all have same values of X. You know, barium sulfate is insoluble in water. Calcium sulfate XH2O, the value of X for calcium sulfate is 2 because CaSO4 forms dihydrate, and MgSO4 will have 7 molecules of water of hydration. MgSO4 7H2O is also called Epsom salt. It is associated with 7 molecules of water of hydration because of its small size, and hence because of the small size of Mg2 plus ions they are extensively hydrated, and the value of X, which is 7 for MgSO4, and that is the maximum, and hence the correct option is option A. Move on to question number 56. If you react 30 gram of magnesium and 30 gram of oxygen, when magnesium is burnt in oxygen, you get MgO, and the residual mixture contains, the options are 60 gram of MgO, 40 gram of MgO and 20 gram of oxygen. Option C 45 gram of MgO and 15 gram of oxygen. Option D 50 gram of MgO and 10 gram of oxygen. From the equation 2 Mg plus O2 gives 2 MgO. 2 moles of magnesium, that is atomic mass of magnesium is 24, and therefore 2 into 24 grams of magnesium, that is 48 gram of magnesium, will combine with 1 mole of oxygen, that is 2 into 16 grams or 32 gram of oxygen, during which you get 2 into 24 plus 16, 24 plus 60, that is 40 happens to be the molar mass of MgO. So that means to say, from the equation 48 gram of magnesium on combustion or on reaction with 32 gram of oxygen produce 80 gram of MgO. But we are not reacting 48 gram and 32 gram. Here the problem says we are reacting 30 and 30 grams. Obviously, when 30 gram of magnesium is made to combine with oxygen, out of 30 grams only 20 gram of oxygen is sufficient, because 48 gram will react with 32 gram of oxygen, and therefore 30 gram will react with what is called only 20 gram of oxygen, and hence 30 gram of magnesium require only 20 gram of oxygen, and on combustion it produces 50 gram of MgO. Naturally, the residual mixture will be 50 gram of MgO, which is the product, and 10 gram of oxygen, which remains unreacted out of 30 grams of oxygen, because so the magnesium is totally consumed here, and therefore the residual mixture will have only MgO and 10 gram of oxygen, and the correct option becomes option D for question number 56. Moving on to question number 57. The interaction of 3.42 gram of an alkali metal with water liberates 448 ml of hydrogen gas at STP. The alkali metal is, the options are lithium, sodium, potassium, and then rubidium. You know, all alkali metals will definitely react with water and they form metallic hydroxides. So the metal on reaction with water will have the vigorous reaction with water, for your information, forms metallic hydroxide, and in the process hydrogen gas gets liberated. From the balanced equation, it may be noted that 2 moles or 2 gram atom of metal on reaction with water produce 1 mole of hydrogen gas. So that means to say, so the 1 mole of hydrogen gas or any gas at STP will have a volume of 22.4 liters or 22,400 ml. From the information which is given, 448 ml of hydrogen gas is liberated by the reaction of 3.42 gram of the alkali metal. Therefore, 1 mole of hydrogen gas or 22,400 ml of H2 gas is liberated by 3.42 divided by 448 into 22,400, and if you simplify this, it comes to 171 gram. That means to say 171 gram of metal on reaction with water liberates exactly 1 mole of hydrogen gas. So this 171 gram is produced from 2 gram atom of the alkali metal, and therefore gram atomic mass of the metal becomes 171 by 2, that is equal to 85.5. So the atomic mass of the alkali metal is 85.5, which is definitely what is called heavier alkali metal like rubidium, which is there in the option, because lithium, sodium and potassium are all light metals, and therefore the rubidium with option D becomes the correct answer. Moving on to question number 58. Which of the following carbonates will not decompose on heating? The options are option A calcium carbonate, option B sodium carbonate, option C barium carbonate, option D cadmium carbonate. And among all the 4 options, the only alkali metal carbonates, the exception for that is again lithium carbonate. Only alkali metal carbonates do not decompose on heating. In the 4 options which are given, calcium carbonate, barium carbonate, cadmium carbonate, they are all not regarded as alkali metal carbonates. The only what is called alkali metal carbonate in the 4 options is sodium carbonate, and that will not decompose on heating, and hence the correct option is option B. Moving on to question number 59. Which of the following is most commonly used in photoelectric cells? The options are lithium, francium, potassium, and then cesium. See, in the alkali metals, when you go down from lithium to what is called cesium or francium, from top to bottom the values of ionization energy decreases because of increase in size. That means to say, the valence electrons of cesium can be easily removed, and therefore cesium is the metal which exhibits what is called photoelectric effect. So as you know, the emission of electrons when the metal surface is irradiated to solar radiation. Cesium is one such metal which can easily give out the electrons from its surface because of its extremely low value of what is called ionization enthalpy. Though francium has lower value of ionization enthalpy than cesium, francium is a liquid at room temperature, and therefore cesium is most commonly used in what is called photoelectric cells, and therefore the cesium with option D becomes the correct answer for question number 59. Moving on to question number 60. Which of the following statements is correct? You have to find out the correct statement among the four options. Option A, alkali metals are less electropositive than alkaline earth metals. Definitely this is not an acceptable statement, this is a wrong statement, because alkali metals are more electropositive than alkaline earth metals, because electropositive character decreases when you move from left to right of the periodic table, and obviously this is a wrong statement. Alkaline earth metals are denser and harder than alkali metals. Definitely this is a valid statement, because alkaline earth metals will have small size when compared to alkali metals. When you move from left to right along a period, because of the addition of electrons to the same shell and increase in the nuclear charge, the size naturally decreases, and therefore alkaline earth metals in each group will have smaller size compared to what is called alkali metals. So, and the higher mass of alkali metals, alkaline earth metals, makes it to be denser and harder than alkali metals. Option B appears to be the correct statement. The correct answer for this question, as I said, is option B, but when you look at the option C and D, option C says alkali metals are denser and harder than alkaline earth metals, which is incorrect statement, and the first ionization potential of alkali metals is more than that of alkaline earth metals. This is again incorrect statement, because the alkali metals will have what is called the less ionization potential because of NS1 configuration. Therefore, the option A, C, D are incorrect statements, and it is only the option B which is a correct statement, and hence the correct option for question number 60 is option B. Right, with that we come to the end of this session on the hydrogen S block and group 13 and 14 elements of P block, and I thank you for watching this class, and I thank all the authorities of Department of PU Education for providing me an opportunity to what is called express my what is called views and help the students in gaining the knowledge in these chapters. Thank you very much.